Sky high, fighting off the spaceships, and so you're drinking in your room to make it all. It didn't end too soon. You got the next.
All right, so let's try an example of this. What we're going to do is find a point on the plane. So now we're starting with a plane. And I'll give you the equation for that. That's going to be x over 2 plus y over 4 plus a z over 4 equals 1. Closest to, okay, hold on. Let me try to spell here. Closest to the origin in R3. Okay, R3 meaning space in 3 dimensions. Okay, so what this is here, let's see what are we doing. First of all, we have to identify what is our main function, what are we trying to optimize, and then on a side note, what is our constraint curve? What are we limited by? Okay, so first of all, what we're going to do is find a point on this plane closest to the origin. So closest means that we're minimizing the distance, right? So we're minimizing the distance to the origin. So first of all, how do we represent the distance to the origin? We're going to have f of x, y, z this time because we're in R3, right? So we have to have 3 variables. So this is going to be x squared plus y squared plus z squared, and then all under a square root sign. Okay, so this is the distance formula, and what we want to do, this is our main function that we want to minimize. Okay, and then on a side note, we're going to identify what is this then. This is our constraint curve. It's showing us what it's going to be, right? But so instead, this constraint curve, we want it to equal 0, right? We have to have g of x, y, z is equal to 0. So what we're going to do is subtract the 1 over to the left side. Okay, so we're going to have x over 2 plus y over 4 plus z over 4 minus 1 equals 0. Okay, so now we have it. This is the formal, the proper way to write it. Okay, so g of x, y, z. So that's our constraint curve. All right. So now, what's important to note is actually that when we look at our f of x, y, z function here, it has like the square root of 3 variables being squared and then added together, right? So this square root, that's going to be super messy when we try to find the partial derivatives. So it's important, again, to realize that when we're minimizing the distance of something, we're also minimizing the square of that distance, okay? So here's an important point. Minimizing distance, I'll abbreviate, is the same as, it has the same effect as minimizing the distance squared, okay? Distance squared, okay? So I'll show you what I mean by that on the next slide. So as opposed to having our original f of x, y, z, our distance formula, or our distance function being this, what we're going to minimize instead is our new f of x, y, z, which is going to be just simply x squared plus y squared plus z squared. Okay, that'll make it a lot easier instead of having this hindersome square root sign in the front. Okay, so that's what we're going to be looking at instead. So that's our f of x, y, z, and again our g of x, y, z is x over 2 plus y over 4 plus z over 4 minus 1. Okay, so now we're going to make use of our Lagrange equation, right? So we're going to have the gradient of f at a certain point should be equal to lambda, so that's our multiplier, our Lagrange multiplier, times the gradient of g at some certain point. Okay, so our goal for this is to find that point P at which they're equal. Okay. Alright, so this is how we're going to do it. First of all, we're going to find the gradient of f and then find the gradient of g, and we'll go from there. So the gradient of f, looking at this guy, so the gradient of f is going to be simply, we're going to have f sub x, f sub y, and f sub z. So the first one, we're going to take the partial with respect to x, so the y and z terms go away, they disappear, they go to 0, and we just get a 2x. For the y term, we have 2y, and for the z one, we have a 2z. So that was a lot simpler, right? Without that that nuisance, or what do you call it? Well, I'll just call it without the really annoying square root sign, right? So anyway, so that's our f gradient, the gradient of f. And now if we take the gradient of g, we're going to have g sub x, g sub y, and g sub z. Okay, so that's going to be, if we look at our equation up here, this one up here, if we look at the coefficient of x, that's just a 1/2. Look at the coefficient of y, that's just a 1/4. And we also have another 1/4 for the coefficient of z. And then that -1 kind of just goes away every time we take the partial derivative, right? So this is what we have, and now I'll show you how to set up our equation. So what we want is the gradient of f at some point equal to lambda times gradient of g at some point. So we're going to fill in, the gradient of f was 2x, 2y, and 2z. Okay, and then we have lambda times a 1/2, and then a 1/4, and then another 1/4, right? So now what we're going to do is I'm just going to distribute the lambda into each of those, okay? So we have 1/2 lambda, 1/4 lambda, and another 1/4 lambda, okay? So now what we're going to do, since these are equal, equality means things should be equal, right? So what we're going to do is set the components equal to each other. So the x components here, so as first components, we're going to kind of create mini equations. So we're going to have 2x should be equal to 1/2 times lambda. Now let's set the second ones equal to each other. So now we have 2y should be equal to 1/4 lambda. Okay? And then finally we have 2z and the 1/4 lambda. So then we have a 2z should equal 1/4 lambda. Okay? And now, from this point, once we created these mini equations, what I'm going to do is solve for lambda, okay? Because lambda, it should be the same lambda for each of these equations, right? So what we're going to have is lambda is equal to 4x, okay? Lambda for this one is equal to an 8y, and lambda for this one is equal to an 8z, okay? So here, now we have a different kind of equality. We have a lot of equalities going on, right? So lambda should equal 4x, lambda should equal 8y, and lambda should equal 8z. And since these are all the same lambdas, we can basically set everything on the left side equal to each other. So now we have that 4x is equal to 8y is equal to 8z, okay? And we did that via the lambdas, okay? So here we didn't even have to know what lambda was, really. We don't know if it's 2 or like 500 or anything like that. We kind of just used it as like a thoroughfare or a pathway to get to what we wanted, which was a relation between x, y, and z. Okay, so now I'm just going to divide by 4. Well, I'll just divide by 8, and we'll see what we get. So we have 1/2 x is equal to y is equal to z when you divide everything by 8. Okay, so now we have equations between all of our variables, okay? So now we have that y is equal to z. So z just equals z itself. Z is equal to y, and z is equal to 1/2 x, okay? Also known as x is equal to 2z, okay? So now we're going to take these relations and plug them back into the constraint equation, okay? So I'll rewrite them on the next slide. So we know that z is just equal to itself, we know that y is equal to z, and we know that x is equal to 2z. So here I just kind of wanted to narrow everything down and eliminate everything but that one variable. So we're going to get everything in terms of z. That's what I'm going for, okay? So let's look back at our constraint equation. And this one was x over 2 plus y over 4 plus z over 4. And then minus 1 is equal to 0, right? So something like that. That's what we had for our constraint equation. That was the equation of the plane. And now what I'm going to do is plug in the z stuff in for the x, y, and z respectively. So in for x, I'm going to plug in this 2z over here. So 2z over 2 plus, and then in for y, I'm plugging in a z. So z over 4. Then we have a plus, and then this also, that's just going to stay z over 4 minus 1 equals 0. Okay? So now this one goes away, but we can actually, instead of just crossing that out, I'm going to make a common denominator. So I'm going to make that a 4z over 4. And then we have plus z, and both of those are over 4. Okay, and then I'll just move that 1 to the right side. Okay, so now on the left side, we actually have a 4 plus 1 plus 1. So that's a 6z over 4 is equal to 1. So if we multiply by the reciprocal, we get z is equal to 4 over 6, which is the same thing as 2 over 3. Okay, so now we found that z equals 2 over 3, so we found one of those values. That's good. And now we can go back to these relations up here, and we know that y is equal to z, so y also must be equal to 2 over 3. And we know that x is equal to 2 times whatever z is. So 2 times 2 over 3, so that would be a 4 over 3. Okay, so that's basically going to be it. These are our coordinates here. So the point at which we can minimize the distance to the origin and still stay on the plane on this constraint equation, right? Still stay in line with that, is the following. Our x is 4 over 3, our y is 2 over 3, and our z is 2 over 3 as well. Okay? So sometimes, believe it or not, there is more than one constraint equation or more than one limitation on how far you can move and which way you can move. So in that case, every time you have an additional constraint, so for every additional constraint equation, or just constraint, right? So for every one of those, we're going to add another multiplier, another Lagrange multiplier. And what I mean by that is the following. So let's say, before our Lagrange equation looked like this. So we had gradient of f at p is equal to the lambda times gradient of g at p, right? So this was one of our constraints, right? One of our constraint equations, and this was our first Lagrange multiplier. Now, if you have another constraint equation, let's say we have some like, so for every additional constraint, so let's say we add in some kind of like h equation, h of x, y, z, or something like that. So then we would add on a whole nother term which has the gradient of that equation, of that constraint equation at that point, times another Lagrange multiplier. We're going to add that guy in. Okay, so this term is completely extra. When you add in another constraint equation, you have to add in another Lagrange multiplier. So things do get a little bit more complicated every time you keep adding on something, 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 right? But that's kind of just naturally, right? So anyways, and then we would just solve again through like system of equations or something like that. Okay, so we will do an example of this in the practice problems video. So that's it for this video, for this concepts 1. I hope that helped, and good luck on your homework.